It's my friend Max Raginsky, and he's also somebody who's too broad to try to characterize. I say what's actually here, which is used by the intersection of control. You can tell me what I'm leaving out.
Life, meaning of universe, that sort of thing.
Verban. One thing is verban.
Verban, yes. Is this thing on?
Yeah, I think
it's on. Okay.
So Max Raginsky, now at the University of Illinois, speaking on online discrete optimization and social networks.
Oh, Max, are you using my?
No, this one's yours. Your adapter, right?
No, it's a
Plug it. It's not plugged in.
I'm not plugged in. Okay, so I'm sorry. I apologize for having to switch the talk title on you, but it was actually a serendipitous occurrence because the ideas in this talk are closely related to what Ramon was just talking about: Markov random fields, some statistical physics ideas, and this is sort of one of my first forays into things that are genuinely discrete. My training originally was in mathematical physics, continuous things, operator spaces. So I'm much more comfortable with continuous objects. This is a foray into discrete things. And what's even more remarkable is that my collaborator, Angelia Nedic, who's an optimization and distributed optimization expert in the industrial engineering department at Illinois, that was her first foray into discrete things. So we'll see how this works out. So let's think about a very messy problem: decision making and optimization in large networks of agents with different capabilities, different information, different authority of what they can do with that information. So this is sort of the subject of considerable interest in social sciences, quantitative social sciences, and economics. In machine learning, you have ideas related to crowdsourcing and recommender systems when you're trying to aggregate preferences of multiple users. And traditional analysis of this relies on sort of very classic assumptions related to rationality and knowledge. So the standard classic analysis assumes that you have a network. And I'm being very broad and very vague, but you have a network. Each node is some sort of an agent, sentient or not. Could be machines or humans. Each agent is observing some signal related to some underlying state of the world. The world is stochastic. The agents know the probabilistic law governing the world. They know the probabilistic law governing their observation given the state of the world. And typically, the idea is to try and extract some sort of utility, and they do that by acquiring signals about the state of the world and then acting on them. So there are several assumptions that one can question, especially in the realm of economics. And the assumptions pertain to, first of all, the knowledge of the stochastic model. You can't really I think in 2008 we saw all too clearly that all the fancy models that the Wall Street people use are completely disconnected from reality. Although, if you believe that compensation is connected to your knowledge of reality, the bonuses somehow reflected. Maybe they got rewarded for whatever model they had. Somebody optimized very well. Right. So and also you assume that the agents select actions by looking at the information that they receive pertaining to the state of the world, and then are essentially endowed with infinite computational capabilities and maximize utilities. As my friend Cosma Shalizi from CMU likes to say, perhaps a little uncharitably, typical economic agent is modeled as a hedonistic sociopath who can solve NP-complete problems. So the main question there is, do the agents acquire enough information in order to learn something about the underlying state of the world? So if we relax these assumptions and try to model things that are slightly closer to reality, first of all, there is no such thing as a static parameter or a random process that describes the world. The world gives you information about its current state, but you can't really assume a probabilistic model for it. Even if it exists, certainly no single agent is capable of it. And if we have, a largely decentralized, let's say, economic or social system without, any totalitarian control, then nobody can really tell you what that model is because, maybe the NSA has it. I don't know. Probably not. But instead, what happens is the environment affects the agents through some cost related information. So you take an action and you see the consequences of that action. So you're free to use that historic data to decide on what to do next. And this is indeed, the essence of life, right? You learn from experience continually and you never stop, presumably. And no agent has a probabilistic model. And moreover, agents, well, let's say, typically people have inertia. You tend to stick to a particular mode of behavior if it has worked so far and you have no strong signal compelling you to do otherwise. People are lazy or, preferences are sticky. That's just an empirical fact. So how can we account for some of that? And then there's also, of course, the social network aspect, meaning that, typically information is shared not globally, but you talk to your friends, you talk to your neighbors, and this is how information spreads. So locality of information exchange is also a fact. So let's see, first of all, what we can talk about for a single agent that has inertia. So right now I'm only modeling the fact that you have an agent that tries to minimize costs, but unless there's a sufficiently strong reason to stick to some explicitly cost-minimizing behavior, the agent will just prefer to do something by default. So you can think about the problem of suppose you have a finite set of alternatives that you have to choose from, and I'll call that X. The agent is going to select one of the alternatives at random according to some probability distribution pi that is to be optimized. And the way you optimize is you say, okay, well, here's what I would incur on average. So the cost of different actions is quantified by some function f. This is the expectation of my strategy, right? The expectation of the cost with respect to the strategy. Or strategy is distribution over actions. So if I didn't have inertia, clearly I would pick the action with the smallest cost. Just have a Dirac measure concentrated on the action with the smallest cost. But because I have inertia, in the absence of any other signal, I have some distribution mu naught that tells me, in the absence of all other information, all other signals, I will tend to select actions according to some fixed distribution mu naught that characterizes me as an agent. So what I do is I minimize a combination of the actual cost and the inertia term. The inertia term just tells me it's a relative entropy, right? The Kullback-Leibler divergence. It's large if I end up selecting a strategy that's too different from my default strategy. And beta is a parameter that characterizes the trade-off between these two things. And here I assume that each action has a non-negative, a positive probability of being selected under the default strategy. Well, I can solve this in closed form. It's actually trivial, but economists like this model. It's called the multinomial logic choice model. And it's studied quite extensively, although I don't think that they ever wrote down this optimization problem for it. So multinomial logic choice arises naturally when I have to balance so the tendency to get, the need to get off the couch to minimize costs versus the, utility of staying on the couch and watching TV. So that's that. So this term is small if I actually prefer to, not stray too far from the couch.
I presume you chose that optimization problem so you can get the answer.
Oh yeah, absolutely.
So this is a good variation principle.
That's a good variation principle, exactly. Right. So now let's think of now let's add one element. Still a single agent, but now there's this environment that the agent is interacting with. The agent is, again, think about, again, an individual does not really model the environment stochastically. You take an action, you observe the consequences that could have resulted from, different actions, and that's your cost at time t. At time t plus 1, the costs might be completely different. The world may have changed, but, you're going to use knowledge of previous consequences, previous states of the world to decide on what to do next. So you can think about a time-varying sequence of cost functions from some class f, script f, which you fix, but you have no assumption on the evolution of the sequence. It's revealed to you causally, right? You take an action at time t, the function f sub t, that describes the picture of the world at that time instant. There's there could be a model that's driving the evolution of f sub t's. You have no idea of that model. And so you're going to select a strategy pi sub t at each time t that depends only on the historical data. And the historical data is just the snapshots of how costly it is to take various actions at different times. So at time t, you incur this instantaneous cost that has the two terms, the inertia parameter times the expected cost plus this plus the price you pay for deviating from the default. And the default strategy stays fixed. So here, because of the non-stochasticity of the environment, you have to kind of move the goalpost a little bit. And now you want to minimize a quantity that's called the regret. So the regret is you take your running cost, right? So at time t, you draw an action according to pi t, and you incur the cumulative cost lt. That accounts for minimizing the actual cost ft versus sticking to the default. If you had known all the snapshots of the world, the profiles of the world up to time capital T, and could choose one single strategy to just use at every time t, you could probably have a more sophisticated thing. If I can switch between, if I switch my strategies fixed number of times, I can optimize with respect to that. This is the simplest setting. You compare your causal performance, so what you actually can incur as the world unfolds around you, versus a clairvoyant type of an agent that could see all the costs ft ahead of time and plan ahead. So, and this has this idea has been around since at least seminal work of James Hannon on essentially approximating equilibria in games with unknown structure by observing empirical frequencies. So the goal is to ensure that as time goes on, your per round regret goes to 0 no matter what snapshots the environment generates, no matter what the world does, as long as you're in some sort of a well-structured class of functions. And of course, you're also interested in rate of convergence of this quantity to 0. So this is a single agent. Now let's look at social networks. Okay, so now what we're interested in, the situation where you have a large number of agents, and each agent also takes actions in a set of a large number of alternatives. So each agent has to choose between q different actions. Q is large, n is large. So your overall, for the entire network, the action profile of the network is an n tuple of integers from 1 to q. And we'll also assume that the cost functions decompose into sums of 1 and 2, sort of two variable local terms, which means that every time each agent takes an action, that action affects that agent directly, and also affects that agent and their neighbors in the network. So now we have this sort of trade-off between selfishness and a little bit of local altruism, and each agent only receives information that tells the agent about the costs of that agent's actions and the actions that affect that agent directly from the neighbors. Right? So you don't know what happens to the world outside of your immediate neighborhood. So the goal, there are two goals. So one is we want to actually develop a low regret strategy that respects the information structure, and two, we want to make sure that the achievable regret scales favorably with all the parameters of interest. In particular, we want it to scale sublinearly with the time horizon so that you have Hannon consistency at the very least. Right? You scale the regret by time horizon, it goes to 0. But you also want polylogarithmic dependence in terms of network parameters, number of vertices, maximum degree, etc. And this is just sort of tradition. That's what you want. It's decreed that things should be polylogarithmic in network parameters. Okay, so here's our model. We're going to assume that we have a graph, G.
Polynomial of a logarithm or
Polynomial of a logarithm, yes. So we have a graph which describes the network. It's a simple undirected graph. I don't assume that the graph is connected. And some notation, I have a agent V, the neighborhood denoted by this nice boundary symbol is just all agents that are neighbors of that agent, and then we have a maximum degree. This is the action space, of course, as we said, just tuples of integers from 1 to q, and we have a default strategy. So in the absence of any other signals, each agent just tends to do their own thing independently of others. We assume that, again, each default strategy of each agent puts positive mass on every action. And then we'll also have a class of cost functions that are of this form. So these are the terms that affect each individual agent separately. And then we have these two variable terms that affect pairs of agents. And then we have two fixed classes phi and psi that constitute allowed classes of 1 and 2 agent costs. Okay, so this is kind of just a cartoon that shows you what happens. Okay, so how do the agents interact with the world? So first of all, we assume that at time 0, each agent takes an action by default, independently of all others. And then what happens at each discrete time? At time t, one agent is activated uniformly at random. You can think about sort of the environment somehow, contacting one of the agents completely independently of everything else uniformly at random. That agent then gets to go. It gets to make a move. So now the agent selects an action on the basis of all of the current information that agent has. And other agents simply just stick to what they did before. So other agents replay their past actions. And then after that, each agent then observes current costs that affect that agent, right? So each agent observes the new individual cost and the new costs connecting that agent to the neighbors. And then the system proceeds to the next round. So in fact, static variants of this, where the cost functions are fixed, and now we're looking at time evolution, we're studying, of course, in statistical physics, this is just pairwise Markov random fields, but in economics, actually, there are two papers by Bloom called Statistical Mechanics of Strategic Interaction, which are basically nothing but taking more or less the Brownian uniqueness theory and rewriting it in economics terms. I mean, really, that's all it is. We're trying to understand the emergence of institutions. At least that's the claim in the papers. But in evolutionary dynamics, there's a beautiful work by, say, Bill Sandholm on trying to embed these models into some what's called revision protocols. You look at evolution of traits in a large population using these models. But now what we have is we have this online aspect. In other words, when you take an action, then the new costs are revealed to you ex post facto, and you don't know ahead of time what they will be. Okay, so this is just, again, this shows you what agent V sees at time t, sees its current cost plus the cost to connect that agent to the neighbors, and this is the entire cost for the entire network, and this is the information update rule for agent V at time t, right? So previous information and then the costs that are revealed at time t about the neighborhood, and then also the actions of everybody in your neighborhood, okay? So what's the goal? Now we're going to assume that we fix a sequence of the environment generated cost functions. The agents don't know it, but what's crucial here is to assume that there's no feedback from the agent's actions to the cost functions. In other words, from the environment's point of view, its evolution is predestined since time immemorial. It's just some sequence, but the agents don't know it. It's revealed to them causally. You can actually show that once you allow the environment to feed back on the agent's actions, all of this will spectacularly break down. So it's not clear what to do in the case of slightly reactive environments. When the environment is fully informed of the agent's past actions, there's nothing you can say. You can construct counterexamples that break everything down. And now we describe the whole thing in terms of stochastic evolution, right? So let mu sub t denote the distribution of the action profile of the entire network at time t. And the initial condition, of course, is a product measure comprised by the default distributions. And the stochastic update takes this form, right? So one agent is activated uniformly at random. That agent gets to update its action based on the local information it receives. Everybody else sticks to what they did in the previous time step. And so, of course, I will describe that. So we have the evolution of these measures in time, right, through these time-varying, time-inhomogeneous Markov chain. And now the goal is to design a local update rule that respects the information structure to minimize this regret. So the regret is so the network with the decentralized structure is scored against a centralized entity that could direct all the agents on what to do. If it had all the local information, it could just tell the agents, do this.
What do you do in the absence of information? Because you're not allowed to adapt it to the past, right? It's not a predictable strategy, it's a fixed strategy.
Right. This is a fixed strategy. I mean, so the thing is that in these regret problems, you can't, there's a danger of, kind of biting off more than you can chew, because, if I allow arbitrary strategies here, arbitrary time-varying strategies, there's no way to compete against something like that. It'll just memorize what the environment is doing. You'd have to restrict the comparison strategy somehow. You could, restrict its complexity. You could say it's a time-varying strategy, but it's piecewise constant with this many switches per time. You could do that. It adds technical complexity, not much in the way of insight. So let's just analyze, just time-invariant strategy. By the way, how much time do I? Sean? How much? 25 minutes. Oh.
What is script F?
Script F is the class of all functions of this form, where the 1 and 2 variable potentials come from two fixed classes. So I have two fixed classes of 1 and 2 variable potentials.
This would be a smooth class. I mean, a small class.
Well, these are they act on finite sets. It's a small class. I assume let's suppose it's just a cube in R.
Okay, like just uniform bounds.
Uniform bounds. Yeah.
Okay.
Okay. So this is the problem, and this is the main result. So suppose the following conditions are met. So the local costs are all bounded uniformly. Let's say between -1 and 1. Just, and also assume the inertia parameter beta, which is that thing that multiplies the cost term versus the inertia term. The inertia parameter beta times the maximum degree has to be less than 1. High temperature. The time horizon t has to be sufficiently large, and this is just a memory type of effect. So you see that the time horizon has to be sort of at least cubic in number of vertices, and then log 1 over theta makes an appearance. Theta is the minimum probability of any default action at any agent. And if that's the case, then there exists a decentralized strategy that achieves this regret scaling. Here, tilde over the big O hides polylog factors. So, so for example, if something is here, in fact, this could be something like this times some power of the log of that. So decentralized in the sense that each agent's knowledge is local. So when I take an action, I only know the cost function that affects me and my neighbors. I don't know the cost functions that affect my neighbors' neighbors, et cetera, et cetera. So decentralized in that sense. And you can see, so let's look at the scaling with respect to the time horizon. It's square root of t, and as we'll see that's the best you can hope for in the centralized case. However, now you also see that you're proportional to this inertia parameter, proportional to the maximum degree, and then you have, super quadratic dependence on the number of vertices. And then there's this is sort of again, the kind of a mixing rate type of a thing. But so we have, in fact, achieved the goal. We have polylogarithmic dependence on the network parameters and sublinear, in fact, optimal dependence on the time horizon. So now, I'm going to briefly describe how this is proved, but first let's look at some sort of comments on what all of this means. Yes.
Quick dimensional analysis. So typically, what you expect in a high temperature regime. But I'm not thinking about strategies. I'm thinking about Gibbs measures. Let's say.
Right.
So typically, what you expect in a high temperature regime is that basically the pressure stabilizing. So if you take the log of so your cost is basically the log of the position.
Yes.
So this should be of order of the number of vertices.
Right.
So, but here you have vertices to the 5 halves.
Right.
So I'm curious whether that's an artifact of the proof, or whether really you pick up an extra 3 halves of, from the fact that you're doing optimization, or what?
So it's
what you expect, right?
Square root of t is what you expect. Right. So the part of the dependence on the number of vertices comes from the fact that there's this relative entropy term, and so the idea is, so here's a proof strategy. I'm first going to construct a centralized strategy and bound its regret. Now what I'm going to do is I'm going to use the Glauber dynamics to approximate the centralized strategy. And that Glauber dynamics, but the thing is that Glauber dynamics is time varying because the centralized strategy is time inhomogeneous. Okay. So at every time step, I only do one step of the Glauber dynamics. Then I have to redo everything because the cost functions change. I can't mix. So that's the penalty for this sequentiality. Because in the usual Gibbs measure situation, what happens is that your potentials are constant.
Yes.
So that means that you can essentially run the Gibbs sampler for a Glauber dynamics for as long as you want until convergence. Here you cannot. You only get to, so you actually see this when I discuss the proof. Okay, so
Is it optimal or?
most likely not. So the dependence on these parameters is most likely not optimal. Okay, so first of all, the interesting thing is that we do not require the graph to be connected. If you have an isolated vertex, that vertex is going to be activated every once in a while, and it's going to waste everybody else's time, because that vertex gets no signals from anybody else, and nobody else gets signals from that vertex because there are no edges connecting it. But what's going to happen is that every once in a while it's going to be activated, everybody else is idling in the meantime, so that's going to affect regret. Right?
Also in a trivial way, right?
In a trivial way, meaning that
Disconnected, that all the points don't talk to each other.
Right,
You
exactly.
just multiply the regret by v.
Exactly, yes.
So that would be a better bound than you have. You have v to the 5 half. I mean, this, yeah.
No, but that's exactly what's going to happen, right? That v to the 5 halves, that's exactly what, you have v to the 3 halves in the centralized case.
Oh,
Yes.
then v to the 5 halves is probably optimal, because even if you have no connections, it's going to be.
I'm not sure if v to the 3 halves in the centralized case is optimal either.
That's where the cost is.
Yeah. Okay, so the first regularity condition, this beta delta less than 1, that's actually a Dobrushin uniqueness condition. I mean, that's with a twist. But it means that essentially agents must have some amounts of inertia that actually depend on the maximum degree. So the more neighbors you have, the less emphasis on reacting to the environment you can afford, because the more neighbors you have, the more information you'll get. So that way, the second regularity condition. By the way, remember that beta is an exogenous parameter. It's something that just characterizes the inertia of each agent. The second regularity condition, as we'll see, that just tells you that you have to get first to the point where the effect of the past cost functions on the behavior at time t is washing away with time. There's going to be this interesting inverse discounting going on in the centralized strategy. And also, the interesting thing is that when the default actions are uniformly distributed, the regret scales with q as square root of log q, and that's optimal. Okay, so another comparison, of course, there's a paper by David Gomarnik, David Goldberg, and Theo Weber that I think probably has come out in Mathematics of Operations research. They looked at static optimization problems. So optimization problems of this form, where the functions don't change, the functions are known, but the agents are allowed to talk to their neighbors, their neighbors' neighbors, their neighbors' neighbors' neighbors, up to some radius. And they want to look at the convergence rate of this optimization as a function of the radius. So they construct again, under something like the Dobrushin uniqueness condition, exponential decay of correlations, they show that there exists an algorithm that can epsilon optimize this in time that's polylogarithmic and all the network parameters. So our result is sort of we only allow one-hop interactions, and the functions arbitrarily change in time, but conceptually it's related to this line of work.
This is a zero temperature result, because
this is zero temperature. Yes.
high temperature, so it's almost opposite, right?
Right. Yes. But I mean, so they don't. The thing is that in my case, there is the in addition to these costs, there's also the relative entropy term, right? So it's entropy versus energy type of thing. This is really exactly as you can. This is zero temperature.
No, but in your case, the relative entropy actually dominates, because your beta.
Yes. That's
so
right.
In your case, the relative entropy actually
Yes,
dominates, but
that's
in this
right.
case, the relative entropy is missing.
Yes,
right?
exactly.
So in some sense, these are opposite scenarios.
These are opposite scenarios, but we're sort of motivated by this idea, trying to see what happens. So the relative entropy terms are actually, as I said, they're sort of empirically motivated, because real agents do have inertia. Economic behavior of individuals, going back to Keynes. And the thing is that right-wing economists always reject this notion that prices are sticky, wages are sticky. No, everybody reacts to everything instantly. But no. Anyway, so here's the idea of the proof. So first we're going to construct a centralized strategy that achieves, so here's the convention. Pi always denotes centralized things, and mu denotes decentralized things. So pi t is going to be a centralized strategy that achieves favorable scaling of the regret. And then we're going to construct, approximated by a decentralized strategy that will closely track the centralized strategy at each time. And here the key technical tool is something really nice. It's a notion of a positive Richie curvature of a Markov operator. It's introduced by Jan Olivier. So we're able to prove a really nice lemma about tracking of a time-varying sequence of Markov kernels. in Polish spaces, not just in finite sets, that is an embarrassingly short 3-line proof that makes everything go through very smoothly. And so the idea here is that we have Markov operators pt such that the sequence pi t, there's this invariance condition. At each time t, pi t is invariant with respect to pt, and the pt's are uniformly contracting. Then we can show that if you take these operators and evolve the system through them on the so these operators are the ones that give you the decentralized updates, then the mu t's will closely track pi t's. So that means that the regrets will be similar.
If you looked at the literature on sequential Monte Carlo method, this is exactly what they do.
Right. Yeah, I mean that's exactly.
I don't know how
right.
they prove.
Okay, so here's the centralized strategy. So we choose another, what we call a discount parameter. So suppose that you have, there's no network, everybody else talks to everybody, so it's a kind of, full connections, but the cost still decomposes in locally. So if at time t, you had a previous distribution pi t and ft, that's the most recent cost signal, you're going to choose pi t plus 1 to balance the cost that you would get if you were to just follow, if you were to optimize based on the most recent update, plus, you say, well, maybe my previous action profile was good enough, let's stick to that. So you pay some price, you add a regularizer, right? So this is kind of a inertia term to say, well, what worked in the past, hopefully it'll work now as well. And you can actually solve this in closed form. This is a recursive structure for these distributions. And this is actually similar to kind of scaling of distributions when you do something like Rayleigh entropy. And then you can actually unfold this recursion and obtain a closed form solution. And you can see that these are Gibbs distributions where the energy function, gamma is this temperature parameter, but it also enters into, so what you look at all the past costs issued by the environment and you discount them exponentially into the past. And the reason why that's good, why that's necessary, is when you apply the Dobrushin contraction argument, you're not going to get linear growth of the energy. Otherwise, it's going to completely kill you and you won't have any mixing. Okay, so the performance of the decentralized strategy is really nice. And so first of all, the successive action distributions drift very slowly. This is the relative entropy of the current, and then the next one scales like this. And then you attain this sort of a regret, right? So you have CV, right? You have V squared plus right. So this is a scaling as a function of the parameter gamma, and then so this is for any gamma, and then you just choose gamma to optimize the right-hand side. This is where that 3/2 comes from. So most likely the dependence on the number of vertices is most likely it's suboptimal, but it's not clear what the optimal scaling with the number of vertices in this case would be. Okay, so this is performance of the centralized strategy. Now we're going to decentralize it. How we're going to do it? Well, look at it from the viewpoint of agent V. Agent V only sees a portion of the total cost. This is that portion. The agent sees everybody else's actions, right? You call that boundary condition, so neighbors' actions. So this is the portion of the cost the agent sees. Well, just implement the same strategy from here, but each agent would do that with the local costs only. And then remember that each agent is activated uniformly at random, so if you marginalize out this activation, you get the Glauber dynamics, you get the Gibbs sampler. So now, all we want to show is that this evolution, if in the two cases the networks start with a default action, and then one network evolves according to a centralized strategy, and the other network evolves according to this sequence of Markov kernels, at each time step, the distributions of the action profiles stay close to one another.
Sorry, what is big VT gamma? The potential applying the local update rule? The local update rule?
I'm sorry. Here? Oh, this is the discounted cost. This is that.
Okay.
But only with the local terms. Yeah. So this is the decentralized strategy, and this strategy is actually time reversible for each time instance. So at time t, look at the centralized distribution. This kernel is reversible with that distribution being stationary. But these kernels vary in time because the costs vary in time. So static variance of Glauber dynamics, again, it's the Gibbs sampler in MCMC, but in statistical physics it's used to show absence of phase transitions at high enough temperatures. This is the Dobrushin uniqueness argument. But it's also known as log linear alerting, again, in the papers by Bloom on statistical mechanics of strategic interaction, or in or spatial adaptive play. Peyton Young is another economist who kind of co-opted some of these ideas. So now the key is to show that essentially if we start the two networks in the same initial condition, the default action, and then evolve one in a centralized manner, and the other one in a decentralized manner, we're going to have, they're going to stay close to one another. So this is a centralized strategy, some sort of an update. This is a decentralized strategy, right? And we want to make sure that these two at each time step, the distributions are not too far from one another. So some observations here. The pi t's stay close together. By Pinsker's inequality, we can bound this, right? Because we know that the relative entropy in two successive distributions in a centralized case is small. And we also know that these kernels, because of the Gibbs sampler at each time step, we have the invariance, right? So the centralized distribution at time t is invariant with respect to pt. And the same initial conditions. So what we need to show is that at each time step, the total variation distance between mu t and pi t is less than some delta prime, which depends on all the other parameters. So how much time do I have left now?
Last I checked, it was
Oh, okay. Well, we're doing well.
including questions.
Okay, so this is sort of the seemingly a blunt tool, but it's actually fairly nice. Notion of Richie curvature of a Markov operator. So this comes from recent work by Jan Olivier. So here's and the things that this you can prove for an arbitrary Polish space. So we have a Polish space X rho. So X is a complete separable metric space. Rho is the metric, and we have any two Borel probability measures mu and nu. You can define the Wasserstein distance. For those of you who were at my tutorial yesterday, you saw this. So you look at all joint distributions on x and y consistent with these marginals and optimize the expected transportation, the expected distance from x to y. And so Olivier says that a Markov operator, so we fix a Markov operator P on this metric space and say that P has Richie curvature kappa if you start from two delta functions, two Dirac deltas sitting at 2 points x and y, propagate the Markov chain one discrete time step, look at the Wasserstein distance between the resulting distributions, and you'll see it contracts from the original metric by 1 minus kappa. And you can actually show that this is the case if and only if when you start with any two initial conditions, mu and nu, look at one step of the chain, the Wasserstein distance has contracted by a factor of 1 minus kappa. So the name Richie curvature comes from sort of this picture, which is similar to the notion of Richie curvature in differential geometry. It tells you if you move in geodesics around the manifold, what happens when you look at the sort of local balls around 2 points in terms of the distance between these 2 points on the original manifold. So you can start, from point masses sitting at 2 points. So the Markov chain will smear out a point into kind of a distribution, and you'll see that in terms of the mass transportation, the Wasserstein distance, that this distance has shrunk by a factor of 1 minus kappa relative to the metric between these 2 points.
This notion has existed long.
Oh yeah, absolutely.
This is called spectral gap and Wasserstein distance. Ira and Mattingly, for example, used this to prove regularity of Stokes equation.
Right. Yeah, the utility here, of course, is that if your space is a geodesic space, meaning that you can characterize only what happens for infinitesimally separated x and y. So that in that way, it's actually it corresponds to sectional Richie curvature. But yeah, I mean, this notion, this Wasserstein spectral gap has been studied quite well. The utility here is that you can only look at sort of infinitesimal transitions, and on a graph you can just look at Hamming distance 1. So it suffices to only consider 2 points x and y that are, if you have a graph, action profiles on a graph, it also suffices to look at action profiles at different one coordinate. So the main results, if you have a sequence of Markov kernels that each of them has a unique invariant distribution, and these distributions drift very slowly, and the Richie curvatures of these pi t's are positive uniformly bounded from below by some constant, then if I have some other probability measure and then I start, I take these kernels and I evolve the probability measure through time, through time in homogeneous Markov chain, then essentially if the initial conditions were distance delta, then at time t, the measures mu t and pi t will be separated by delta divided by this Richie curvature. And the proof is actually, as I said, it's really simple. I'm not going to go through it in the interest of time, but it's really simple. And then the corollary is that if f is any Lipschitz function on your space X, then we can compare expectations with respect to pi t's, which are the target distributions, and mu t's, which are the realized distributions for any Lipschitz functions by the Kantorovich-Rubinstein duality, which we saw yesterday in the tutorial. This is the bound. So now we can wrap up the proof. First of all, the Glauber. So what happens here is that at each time step t, you run one step to Glauber dynamics. Because the energy functional changes the next time the new cost update arrives. So this will not mix, but you just hope that it already, each step gets you somewhat, gets you some mixing. So if you put a Hamming metric on your action profile, right? So count the number of disagreements, and then you assume this condition, then the Glauber dynamics in fact does satisfy this. There's a lower bound on a Richie curvature, and then you get this tracking bound. So you see that in Wasserstein distance, the decentralized strategies are close together. Gamma is, remember, the discount factor. So the smaller discount factor, the closer they'll be. And then you can show that decentralized strategy closely tracks the centralized one. So if this condition is satisfied, this condition is needed to make sure that the relative entropies to mu naught between mu t and pi t stay close together, and that's where you pick up additional dependence on the number of vertices. So these are the bounds, and then all you do is just you look at the local information regret and add and subtract the performance of the corresponding centralized strategy. So this we already know, and then we just pay a price for decentralization, and we already analyzed the difference in the linear term and in the relative entropy term. So under the assumed regularity conditions, this is the bound on the regret. And then, then of course you would want to optimize this over gamma, and this is where another suboptimality comes from. This is a transcendental kind of a thing. If I set the derivative to 0, I have no idea how to solve it exactly. So what I do is I pick a suboptimal gamma. I recognize two terms that I can optimize, and I just choose that gamma and plug it in. So most likely this is better than that, but this is kind of an artifact of the fact that this cannot. It's hard to optimize over gamma. Probably up to low.
Perhaps I didn't understand the point. The fact that the Richie curvature is bounded from below comes from the fact that the potential are bounded, or?
Yes, it comes from the fact that the exponential discounting makes sure that at each time step, otherwise you'd have linear growth, right? Because you get more and more cost functions, and you add them up at each time t. Without the discounting, that will grow linearly, and so you will not be able to just get away with this. But because of the discounting, the L infinity norm, the sup norm of the potential discounted potential at each time t is bounded by 1.
Okay, and the second expression, is it essential to consider Wasserstein distance there, or total variation will not work?
Well, in this case, this no, total variation will not work, because total variation is, remember, it's the Wasserstein distance with respect to a trivial metric. Right? It ignores it just collapses all the, it just really looks at two configurations and says they're different. If they're different, you pay a price of 1. So it's not sensitive enough. I mean, so here there, really Richie curvatures. If you're familiar with path coupling bounds in computer science literature for discrete MCMC, then it just suffices to check this condition for any two configurations that differ in only one node. So anyway, so this is sort of the concluding slide, which I will not read because it's right there. Any questions? Just briefly acknowledge the sponsors of this, and then back to this.
Questions?
Yes? Yes, Miriam.
So, fine, thought of this, but could you apply this to doing belief propagation, say, for LTPCs?
Well, I mean, so
You have that exogenous variable, which usually it's very difficult to look, for instance, at changing channel components, right?
yeah. So you're thinking about something like arbitrarily varying channels,
Maybe
and
not an ABC, but something, yeah.
something. Yeah. I mean, that's the sort of online optimization ideas. I mean, they're really ripe for use in information theory. I mean, they're used in universal data compression. This is the starting with Ziev and Markov and but yeah, I mean that's something like belief propagation on locally tree-like graphs. Yeah, it could.
I mean, they're particularly for decoding, right?
Yes. That's right. Yeah.
Have people looked at that? Do you know?
I'm not aware of anything.
I mean, it's a very moronic question, but how does it relate to the stuff that people are doing on multi-arm bandits? Is it because you got a
In multi-arm bandits, when you find out the cost, you know the entire function. In multi-arm bandits, you only know the function value at the action that you took. Yeah. So when you have bandits, you're going to have to add additional randomization to try and estimate the actual function from the inner product.
Yeah, at each time only one agent is changing. In fact, it's local in the sense that
Yes.
you change one agent.
Yes. Yeah.
At each
At each time step, yeah.
and which is picked, this agent is picked at random.
Yes. You can think of it in continuous time. Each agent has a Poisson clock at unit rate. When the clock ticks, the agent wakes up and does something. Right. I mean, the thing is that it would be more interesting to do what's called systematic scan when each agent does this at the same time. But I mean, the analyzing that in terms of the Richie curvature is painful. So I haven't done it yet.
Okay, let's continue discussion during the short break, probably. I think we'll take 20 minutes. So thank Max once again.